Welcome to the Wireless Evolution course. As part of this module, we will take the wireless evolution journey from GSM to LTE. After completing this module, you will learn about different multiple access technologies, GSM architecture, evolution of GPRS from GSM, evolution of 3G UMTS, introduction of IMS in REL 5, evolution of HSPA including both HSDPA and HSUPA, evolution of LTE from 3G technologies, the LTE deployment path available to operators. So, let us begin. Wireless technologies enable one or more devices to communicate without an actual wired connection. Radio frequency is used to transmit the data. Such technologies are rapidly evolving to meet a variety of communications needs, from simple to complex. Wireless communications needs can all be classified in one of three ways, based on the distance they are meant to cover. These include Wireless Personal Area Networks, WPAN, Wireless Local Area Networks, WLAN, and Wireless Wide Area Networks, WWAN. Wireless networks form the transport mechanism between devices and traditional wired networks. WPANs are limited to distances under about 10 meters and include technologies such as infrared, IR, Bluetooth technology, and ultra-wideband, UWB. WLANs cover a local area with distances of individual access points reaching to about 100 meters, and include technologies such as Wi-Fi. WWANs cover even larger areas, using cellular wireless technologies such as GSM, UMTS or LTE. As part of this course module, we shall focus on evolution of cellular wireless technology from GSM to LTE. The wireless industry is addressing exploding data demand through a combination of spectrally more efficient technology, self-configuration, and self-optimization. Consumers are using more and more data-centric applications such as music and video streaming, social networking, cloud-based synchronization and applications, web browsing, and content downloading. The basic fundamental of wireless technology evolution is the data-optimized mobile system, lower cost and better user experience. As we will study in this course, GSM technology supports voice but very limited data capabilities. With the evolution of GPRS UMTS, networks supported both data and voice. The latest LTE technology is all IP-based and voice is carried using voice over IP or VoIP technology. Through the evolution phases, the cost per megabyte of data for the end user is reducing due to advancement in technology. The cost of highest in GSM while it is minimum for LTE networks, thus allowing users to use various content-rich applications at a lower cost. Finally, the technology evolution is leading to higher data throughput with LTE supporting up to 100 Mbps. Also, the latency is reduced from 150 milliseconds in GSM to less than 10 milliseconds in LTE. Both these factors lead to better overall end-user experience. Cellular systems have come a long way since their introduction in the 1980s. The evolution has been from first-generation, 1G, technologies, beginning in the early 1990s, and eventually to current fourth-generation, 4G, technologies. As we discussed, during the evolution phases, technology has evolved to provide higher user speeds and better spectral efficiency to enhance the overall user experience and enable mobile broadband. First generation, 1G, radio networks were analog-based and limited to voice services capabilities only. 1G devices were easily susceptible to cloning and one channel supported only one device at a time. Global System for Mobile Communications, GSM, is 2G technology that offers both voice and limited data capabilities. GSM differs from 1G by using digital cellular technology and time division multiple access (TDMA) transmission methods. GSM offers data transmission rates of up to 9.6 kbps. General Packet Radio Service, GPRS, introduced the packet core network and the cellular network. 2G cellular technology combined with GPRS is described as 2.5G, that is, a technology between the second, 2G, and third, 3G, generations of mobile telephony. It provides moderate speed data transfer by using unused time division multiple access (TDMA) channels in, for example, the GSM system. GPRS offers practical data transmission rates of about 70 kbps. 3G, also called as UMTS, is developed by the 3GPP, third generation partnership project. In Release 99 was the first release of UMTS. It is characterized by change in access technology from TDMA to CDMA. UMTS Release 99 has a theoretical data rate of 2 Mbps, but the practical capacity is 384 kbps. UMTS offers packet-based transmission for text, digitized voice, video, and multimedia content. High-Speed Packet Access, HSPA, is a mobile telephony protocol that helps improve the performance of UMTS. HSPA is normally referred to as 3.5G, is developed by the 3GPP and is specified in its Release 5 and Release 6 document series, with minor enhancements described in Release 7. HSPA is an amalgamation of two mobile telephony protocols, High-Speed Downlink Packet Access, HSDPA, and High-Speed Uplink Packet Access, HSUPA, that extends and improves the performance of existing third-generation mobile telecommunication networks utilizing the WCDMA protocols. The first HSPA specifications supported increased peak data rates of up to 14 Mbps in the downlink and 5.76 Mbps in the uplink. Long-term evolution, marketed as 4G LTE, is based on the GSM Edge and UMTS HSPA network technologies, increasing the capacity and speed using a different radio interface together with core network improvements. The standard is developed by the 3GPP and is specified in its Release 8 document series, with minor enhancements described in Release 9. LTE offers peak data rates of 300 Mbps in downlink, and 75 Mbps in uplink. The base stations need to serve many mobile terminals at the same time, both downlink and uplink. All mobiles in the cell transmit information to the base stations simultaneously, thus causing interference among different senders and receivers. So, to overcome the problem, the multiple access schemes are required. 3 key access mechanisms defined in wireless technology are: 1. Frequency Division Multiple Access, FDMA. 2. Time Division Multiple Access, TDMA. 3. Code Division Multiple Access, CDMA. Frequency division multiple access or FDMA is a channel access method used in multiple access protocols as a channelization protocol. FDMA gives users an individual allocation of one or several frequency bands, or channels, which are separated by sufficient guard band to prevent adjacent channel interference. Time division multiple access, TDMA, allows several users to share the same frequency channel by dividing the signal into different time slots. Each user is given a specific slot. Between different slots, guard time is defined to avoid interference. At a particular time slot, there is no competition in cellular network. 2G/2.5G cellular systems, such as GSM, GPRS and even Edge are based on TDMA. Available spectrum is divided into frequency channels and users are allocated one or more time slots on that channel. Code division multiple access is a digital cellular technology that uses spread spectrum techniques. CDMA is the platform on which 3G/3.5G technologies are built. CDMA does not assign a specific frequency to each user. Instead, every user uses the full available spectrum. Individual conversations are encoded with a pseudo-random digital sequence. CDMA provides better capacity for voice and data communications, allowing more subscribers to connect at any given time. Due to the increasing demand for higher data rate and more capacity, 4G LTE uses more advanced OFDMA access technology. Let us study the OFDMA in more details. OFDM, orthogonal frequency division multiplex, technology is used for high-speed data communications. It is evolved from three key aspects: frequency division multiplexing or FDM, multi-carrier multiplexing or MCM, and orthogonality. FDM technology divides the available bandwidth into many carriers and allow multiple users to access the system simultaneously. Each user transmits their data on a different subcarrier. To avoid interference, guard bands are provided between subcarriers. Since guard band don't transmit any information, they introduce spectrum inefficiency. With carrier multiplexing, user can split the data into multiple subcarriers and transmit them in parallel. In multi-carrier FDM, the user data is converted from serial to parallel. Then the parallel data streams are sent over multiple subcarriers. A higher data can be achieved by using multi-carrier multiplexing. OFDM adds the orthogonal feature to the multi-carrier FDM. Orthogonality means do not cause interference with each other. In OFDM, the subcarriers are defined to be orthogonal. This allows subcarriers to overlap and save bandwidth. Therefore, OFDM achieves both higher data rate and better spectrum efficiency. Now, let us look into OFDMA, orthogonal frequency division multiple access. For the downlink 3GPP chose OFDMA for LTE, which incorporates elements of time division multiple access, TDMA. OFDMA allows subsets of the subcarriers to be allocated dynamically among the different users on the channel. OFDMA allows multiple users to access subcarriers simultaneously. In this example, 3 users share multiple subcarriers. The assignment of subcarriers for a user can be changed at every single time. OFDMA results in a more robust system with increased capacity. This completes the module. Click Next topic from navigation menu.